So we're going to see what I want to show and share here is sort of a really interesting piece of intuition, where you're gonna basically see how can you run an operation against a set of values just by running the quantum circuit once, which is in comparison to classical computing. Let's imagine you want to do an XOR operation, right, or an AND or a NOT. And so if you want to do this against sort of say like 10 values, then you've got to do this, per each value. So what we're going to show here is how you can do that just with one run in the quantum computer, which shows that there's a substantial difference in terms of the speed of doing these calculations. This by itself, in and of itself, is maybe not completely useful. So, but it becomes really handy when you plug it into a sort of a higher level algorithm, like the one that I took this from, which is how to build a quantum KNN algorithm. So this is basically kind of the full circuit. You can take a look at the paper and at so you can take a look at the video where I build that, and then you will also find the paper this comes from. So this is not my idea, but I'm just trying to explain it to you in a way that it's understandable at the intuition level, so you can understand really the difference. So let's just stay at the level of 4 qubits, and what we're going to do is we're going to do an XOR operation. And we're going to do this for all the values at once. So what we first do is we first encode our concept of all values, which is a superposition. So this is basically what this is giving us. If you can see here is just pay attention at the two lowest qubits, 0 0 0 1 1 0 1 1. So this is these are all the values we want to run this XOR against. And then what we're going to be using the other two qubits is to first encode the other value of the operation, and then the actual operation, and then the result. So what I mean by this is this is just an example, okay? So we're gonna do an XOR with 1 0. So this is going to be 1 0. Let me just mark this. So these first two qubits are used to hold all our set of values we want to run the operation against, and the first two qubits are going to have multiple. The second two qubits are going to have multiple functions. The first what we do is we encode the 1 0, which is in our example what we want to do the XOR with. So we want to do 1 0 XOR 0 0, 1 0 XOR 0 1, etc., etc. Right? So you want to do this with all the values, and what the way you do this is so basically you're using control nodes to do that, and if I remember well from that example, it was something like this and like this, and now the control node here and here. So why this makes an XOR? I mean, you can probably reverse engineer that or build that concept. There's probably other ways to do that, but you do this by, you can take a look at the truth table of the XOR and then figure out how to do that. But this is not the point here. So basically what we have now, if you pay attention at the results here, I'm going to see if I can zoom in maybe, because basically this is now, we've applied the XOR of 1 0 against every single value just by running once the circuit, right? And maybe I can zoom in a little bit. It looks ugly, but it's gonna probably help us. So pay attention to this here, this here, this here, and this here, right? The rest is just, we don't care. So if we have a 1, so we said 1 0 XOR 1 0 is, well, 0 0, right? Because both, like, each of the qubits is the same. The one here, so 1 0 0 1, no, sorry, it's 1 0 against 1 1, right? So we've got 0 0 1 because the qubit at the bottom is a 1 and a 0, which gives us a 1 in an XOR. And then you can check the other ones. It's the same, right? So basically, and that's what you've done. So you've basically run the XOR operation against all the values at once. So that should really show what's the potential of these. And then, the more qubits you add here, the more values you can have. This has its limitations. If you wanna encode a really specific set of values, which is not all the possible combinations of values, there's no guarantee that you're gonna find a because you got to figure out a way to get that specific superposition that you want, right? And then it has to be an equal superposition for this to work. So if you want to have, I don't know, the values 6, 8, and 25 in decimal, then you're going to have a hard time finding a way to build that into superposition. So that's going to be tricky. But if you figured it out, then you have a good starting point for building up other stuff within your algorithm, whatever you're trying to solve. Cool. Let me know if you like that. Leave comments down below, and stay tuned for more.